Hello everyone, I'm Norman Wahlberger. Thanks for joining me on this adventure, classical to quantum. We're looking at physics from a mathematical point of view. Today, introducing harmonic analysis on a circle, moving towards the quantum mechanics of the harmonic oscillator, the hydrogen atom, angular momentum, and other things. But we're going to be looking at this harmonic analysis from a rational point of view. So a very novel approach to things. So this is a topic that impinges a lot on rational trigonometry because people always ask me, well, what about, Fourier series? How are you going to study functions on a circle if you're going to dispense with cosines and sines? So from my point of view, trigonometry and harmonic analysis or function theory on a circle are separate topics, and they don't have to be covered by the same technology. But both of them can be developed purely rationally and computably, and that's what I want to explain to you today. So classically, the harmonic analysis on a circle, going back to Fourier, involves the parametrization of the circle involving an angle, typically from 0 to 2 pi. And then there are these Fourier series, like we see here, where we express a function on the circle, say f, in terms of a series of, well, these sort of basic functions, cosine theta, cosine 2 theta, cosine 3 theta, well, along with sine theta, sine 2 theta, sine 3 theta. And there's also a constant here, a0, sometimes half a0. So the ingredients here are, first of all, the angle, which is essentially a transcendental concept that you really require calculus notions to pin down. And then these corresponding transcendental functions, cosine theta and sine theta, which are given analytically by power series, like these ones here. Okay, but in particular, these infinite series cannot actually be exactly evaluated. So they're not, honestly speaking, really functions in the sort of official sense of a function as being something that you input a number and you get out a number. There's also a sort of geometrical understanding of cosine and sine, of course, via right triangle, where we assume we have a meaning to the angle here, okay, and then these opposite and adjacent sides are sine theta and cos theta if we've normalized the hypotenuse to be equal to 1. So here's where the traditional connection with trigonometry appears. So this is the standard story, and we are going to be dispensing with it almost entirely, all right? So I want to present a new understanding of the circle, which is a fundamental object in mathematics, but from a rational point of view, where we are always dealing with objects that can actually be concretely evaluated. Exactly. Okay, so how do we do that? Well, let's start, first of all, with just some basic understanding that you'll have seen me talk about a lot. So we have the unit circle. Its equation is x squared plus y squared equals 1. Here it is in the usual xy plane. The standard parametrization given e of t equals 2t over 1 plus t squared and 1 minus t squared over 1 plus t squared. In terms of this parameter t, which you can think about as being a position on the horizontal y-axis. We're connecting that position with the point minus 1 over here. Notice I'm using 1 bar for minus 1. And this point here that we get then is given by this. So this is a rational parametrization, okay, of the circle, which is to be contrasted with the more usual physics engineering kind of parametrization in terms of cosine theta and sine theta. So this parametrization is not exact, right? If you plug in a value for theta and actually calculate cosine theta, sine theta, you're not actually getting a point on the circle. You're just getting a point nearly on the circle because you're not able to calculate these infinitesimals exactly. So we want to stick with this exact computable story. Now, the circle is so important. First of all, it's important from a geometrical, historical point of view, but it's also an important classical and quantum object. So it sort of lives in both worlds. And we can get sort of a preliminary idea of the transition from classical to quantum by looking at just the circle. So classically, the circle, typically we'll say S1, consists of a continuum of points. Okay? And the transformations that we consider are essentially geometric, like reflections, rotations, and maybe more sophisticated things like projective transformations, like Mobius transformations. In the quantum point of view, S1 consists rather of a linear space of functions, or the emphasis is on the space of functions on the circle. And that's a linear space because you could add functions and you can scale or multiply them. In this case, the transformations that previously were geometric end up manifesting themselves as linear transformations of this underlying linear space of functions. So we end up getting matrix versions of reflections, rotations, projective transformations, whatever. So the picture that we might have is that a function, this thing here in green, sort of roughly suggesting, a function which has variable values at different points on the circle. Okay, we're thinking about that function as itself a single point in some higher dimensional linear space of functions. Okay, so that's an essential aspect of going from classical to quantum. Going from a geometrical object consisting of points to a quantum corresponding object where we're emphasizing a corresponding linear space of functions. Okay, so when we have linear spaces, we have linear algebra, and so linear algebra becomes important. Okay, so these two views of S1 are intimately connected, of course, and they lie at the core of a lot of quantum mechanics, especially when we extend the story to the two-sphere S2 and the three-sphere S3. And each one of these steps, going from the circle to the two-sphere and going from the two-sphere to the three-sphere, is a big step. But first, then, we want to understand S1. So a natural question is, how do we understand functions on S1? Well, what we are not going to do is introduce a parameter of the angle and then talk about functions of that angle. That's not the way we're going to proceed. We're going to proceed instead by considering functions as just restrictions to the circle S1 of Pauli series on the ambient affine space A2. So the circle is sitting inside this affine space, just consisting of affine points of the form x and y. And for us, x and y are typically rational numbers. This is the ambient affine space in which S1 sits. So by far the simplest and most fundamental kinds of functions on the circle that we can consider are just the restrictions of the simplest kinds of sort of functions on the ambient affine two-dimensional space. And those are the bi-polynumbers. So we're going to be talking about some things which are quite familiar to many of my viewers, okay, if you've been watching my various series, but I'm going to briefly review these concepts. So what is a bi-poly? Well, it's it's a way of thinking about a polynomial in two variables without emphasizing the word variable. Okay, so what we want to do is we want to restrict our attention rather to the coefficients involved and think about the array of coefficients as being the fundamental object which encodes the Pauli number. So for example, here we see a generic Pauli number as an array, a two-dimensional array of rational numbers. So we're starting up here in the top left with the degree 0 term. So this A00 here would correspond to a constant term. And then here in this next level, the degree 1 terms, this would correspond to A10 alpha plus A01 beta. So we have increasing powers of alpha as we go down and increasing powers of beta as we go across. This next diagonal here, the degree 2 terms, corresponds to A20 alpha squared plus A11 alpha beta plus A02 beta squared, and so on. So we always agree that there's a finite number of non-zero terms for these Pauli numbers, although later on we also want to consider sequences, so we can talk about Pauli series. Now, for simplicity and to connect with the more usual story, we will often identify these kinds of things with polynomial functions in x and y. But I want to emphasize that the alpha and beta here are not variables in the usual sense. They're just sort of placeholders. So, for example, the polynumber 3 plus alpha plus 5 beta minus alpha squared plus 2 alpha beta plus beta to the fourth, okay, that's not given in terms of variables alpha and beta. The polynumber's name is just p, and this is what it is. But it corresponds to what more traditionally would be called a polynomial function, say f of x and y, where we just replace the alpha with an x and the beta with a y. So then what are these alphas and betas officially? Well, actually alpha is just this particular polynumber that has a 0 in the top and then a 1 below it, and beta is the polynumber that has a 0 on the top and a 1 beside it. Now, for various reasons, we want to ultimately extend this story to higher dimensions. And for that, it's useful to have an alternate notation and call this alpha 0 and call this beta alpha 1. So this connects with my theory of box arithmetic, okay, where I'm developing a whole new sort of convention for understanding basic arithmetic. That's in the Math Foundation series. So anyway, after we've gotten to polynumbers, then there are these higher dimensional things called multinumbers, and we get a whole sequence of things starting with this alpha 0 and then this alpha 1, and there's a whole sequence of them. So there's a natural ordering to the variables or the polynumbers that naturally pair in this story. But we're only going to stick with these two for now. So we'll sometimes use alpha beta for convenience, but we can replace them at any time with alpha 0, alpha 1. So our notational convention is that alpha to the m, beta to the n, this term, which is the same as alpha sub 0 to the m, alpha 1 to the n, can be now more succinctly written as just alpha to the m comma n, where now this alpha is just representing this sort of possible index of variables, right? So it's really a certain power of alpha 0 followed or multiplied by a certain power of alpha 1. We don't have to put the 0 in 1 here because these things are naturally ordered starting from 0. So, for example, this polynumber that we talked about before, so we can now rewrite it as 3 times, strictly speaking, alpha 0 comma 0, plus the alpha is really alpha 1 comma 0, the beta is alpha 0 1, this alpha squared is alpha 2 comma 0, this alpha multiplied by beta is just alpha 1 comma 1. This beta to the fourth is alpha 0 comma 4. And then we could become a little bit more concise and remove this alpha 0 comma 0, just replace it with a 1, so this becomes 3. This thing here is just alpha, and alpha squared is that. So we could write it a little bit more succinctly. But you see there's some potential here for having a sort of consistent and rather concise notation to deal with functions of more variables, which is going to be important potentially when we get to the 2-sphere and the 3-sphere, because we have to go up in dimensions. Okay, so now we've got some polynumbers, some basic algebra. When we want to do calculus, the starting point is with the derivative. In the algebraic calculus, we learned that the derivative was really introduced essentially by Faulhaber before Leibniz and Newton and so on. And there's a purely algebraic way of thinking about it. So our derivative is capital D, and d of alpha to the n is n times alpha to the n minus 1. So that's for n equals 1, 2, and 3. And strictly speaking, when n is 0, this doesn't really make sense because we have not defined alpha to the minus 1. That's not in the world of polynumbers. So we sort of have to separately declare that alpha, or d of alpha to the 0, which is d of 1, is 0. Okay, so this all appears prominently in the algebraic calculus, and we can also talk about powers. So if we look at d squared, alpha to the n, that's the same as d of alpha to the n. So we perform this thing twice. Then we get n times n minus 1 times alpha to the n minus 2, at least when n is equal to 2 and 3. Then we have to make some sort of separate statement saying that when we are applying d2 to alpha 0 or to alpha 1, we get 0. And just extending it in a natural way, the kth derivative d to the k of alpha to the n, well, we just apply it k times. Then we get an n times an n minus 1, all the way up to n minus k plus 1 times alpha to the n minus k, with the obvious meanings, again, when this k that we're operating on is a natural number which is bigger than n. We're going to get 0. Okay, so we've got derivatives, but that was just derivatives with respect to one variable, the alpha, the polynomials themselves. But we actually have these two variables floating around, alpha and beta. So we want the algebraic calculus equivalent of partial derivatives, okay? And we're not going to use Leibniz notation. We're just going to expand our use of the capital D by having some suitable subscripts. So we're going to introduce d sub 0 and d sub 1 as essentially the partial derivatives, if you like, with respect to alpha and beta. Remember, alpha is the same as alpha sub 0, beta is the same as alpha sub 1, so it makes sense that these operators are d sub 0, d sub 1. And so we've already really talked about d, so d sub 1 is the derivative that takes beta to the n and gives us n times beta to the n minus 1. So it's like a derivative with respect to beta. And again, there's conditions. If the power is 0, then we have to separately specify that the derivative of a constant is 0. So now we can extend both d0 and d1 to bi-polynumbers, so combinations of alphas and betas. So we declare that d sub 0, okay, which is like the derivative with respect to alpha, you can think about that, of alpha to the m, beta to the n. Remember, this is more concisely written as just alpha to the m comma n. That this is going to be, we're just going to treat the beta as a constant and just take the derivative with respect to alpha. So we get m alpha to the m minus 1 n. So we get m alpha to the m minus 1 comma n. And similarly, d sub 1 of the same thing, we get n times alpha to the m beta to the n minus 1. So we have a reasonable world in which we can apply these sometimes called partial derivative operators, but they're just derivatives with respect to our basic polynomials alpha and beta. Okay, so here's a little exercise for you. Show that if you have two bipolys u and v, that we have a familiar kind of product rule for any one of these partial derivatives. D sub I of u v equals u d sub I of v plus v d sub I of u. Okay, and now that we've got these d0s and d1s, well, we can apply powers of them. So we can apply d sub 0 to the k, d sub 1 to the l, apply to one of these generic terms. And we can introduce this notation sort of consistent with what we were talking about, right? We don't really need the zeros and ones because we know what the ordering is. So we can just encode the information with a capital D superscript k comma l, acting on alpha to the m comma n. And sort of implicit here are the underlying zeros and ones, which are sort of the building blocks of these things. So what happens when you do this? Well, then you get m times m minus 1 all the way up to m minus k plus 1, applying the d operator k times to the essentially the alpha to the m component. And that gives us an alpha to the m minus k. And then applying the d1 to the l to the beta to the n, get n times n minus 1 all the way to n minus l plus 1, and there's a beta to the n minus l. Okay, so just a little bit of new notation. Okay, it's something to think about. We're using the natural ordering that we get with multi-numbers. So the boxed arithmetic is actually quite important for organizing all of this and gives us a framework for doing this all sort of rather consistently. Okay, so now let's look at some examples. So here is a nice little bi-poly number. Let's call it little q. Let's call it alpha squared plus beta squared, or in our ordered notation, alpha sub 0 squared plus alpha sub 1 squared. Okay, so if we apply d sub 0 to this thing, well, we just differentiating with respect to alpha, so we get 2 alpha or 2 alpha 0. If we apply d sub 1 to this thing, well, we get 2 alpha sub 1, or if you like, 2 beta. If we apply d sub 0 squared to it, we differentiate once again, we get 2. If we apply d sub 1 squared, we apply d again here, we get 2. Okay, so that's fine. And now we can introduce a gradient operator, which is what we get when we combine a d0 and a d1 as a little vector. So if P is a bipoly, we can define this maybe nabla symbol vector d0 comma d1 by the way it acts on a bipoly p is its first component is d0 of p and its second component is d1 of p. So for example, applying this to this q up here, this gradient of q, okay, so it's the gradient of alpha 0 squared plus alpha 1 squared. That's going to be the derivative with respect to alpha 0 is 2 alpha 0, and with respect to alpha 1, it's 2 alpha 1, which also we can write as 2 alpha 0 comma alpha 1. Now, next is the Laplacian, which is going to play a very big role here, which is another kind of combination, but it's the operator d sub 0 squared plus d sub 1 squared. So this is the Laplacian operator. So, for example, the Laplacian acting on q. So we have to apply d sub 0 squared to it, and we add the result of applying d sub 1 squared to it. So d sub 0 squared of q was 2, d sub 1 squared of q is also 2, so the total is 4. We get another bipoly in general. How about the Laplacian of q squared? Okay, so we have to apply d sub 0 twice to here's the square of q, and we have to add result of applying d sub 1 twice to, again, here's the square. Okay, so when we square this thing here, we're going to get an alpha 0 to the 4th. We're going to get 2 times the product, and we're getting an alpha 1 to the 4th. If we apply d0 squared to that, here's the thing that we're applying it to. The term involving alpha 1 to the 4th is not going to figure because that's going to get killed. These are the ones that are not going to get killed. And similarly here, when we square it, these are the ones that are not going to be killed. So the d0 squared acting on this, well, we multiply by 4 and then by 3, so we get 12 alpha 0 squared. That's the result of applying it to this. And over here, we just the derivative with respect to alpha 0, so we get a 4 alpha 1 squared. And here, 4 alpha 0 squared plus 12 alpha 1 squared. So a total, I guess, of 16 alpha 0 squared plus 16 alpha 1 squared, so 16 times q. Okay, now a very important definition. Bipoly P is harmonic precisely when the Laplacian of P is 0. So we're picking out a very important family of bi-polynumbers, the harmonic ones which are killed by the Laplace operator. So for example, here, these guys are all harmonic. 1 alpha, beta, alpha squared minus beta squared is harmonic, and so is alpha beta. But alpha squared plus beta squared, which is what we're calling q, is not. We've seen that already because the Laplacian of q is 4. That's not equal to 0. Now in degree 3, there happen to be 2 more. There's alpha cubed minus 3 alpha beta squared. You can check that that's harmonic, and also 3 alpha squared beta minus beta cubed. You can check that's harmonic also. So the ones that we've listed so far are basically rational analogs of 1 cos theta, sine theta, cos 2 theta, sine 2 theta, cos 3 theta, and sine 3 theta in that order. So what we're getting here is this potential, this possibility of using these harmonic polynomials to sort of get at these more traditional Fourier series sort of ingredients, but in a purely rational form. Okay, so this is a very good direction to go in. So now, to make further progress and to really get at the heart of what's going on, I'm going to introduce a rather novel notation, which I don't think is part of the standard literature. I'm going to introduce a variant of polynumbers called, say, factorial polynumbers, lack of better. So now for an n, an integer, not a natural number, but actually an integer, we're going to define alpha to the n underscore, okay, that expression is going to be alpha to the n over n factorial for n greater than or equal to 0, and 0 otherwise. In other words, 0 when n is a strictly negative integer. Recall the convention that 0 factorial is 1. So when n is equal to 0 here, okay, then we're talking about 1 underscore being just 1, because the denominator in that case is also 1 along with the numerator. Okay, so we now have these variant polynumbers defined for general integers, and that turns out meaning that we can have a consistency with respect to differentiation, which is very pleasant. Okay, so given by essentially this rule here, that if you have an integer n, then the capital D derivative of alpha to the n underscore is equal to alpha to the n minus 1 underscore. You see, because when n is strictly negative, then both of these things are 0, and the derivative of 0 is 0. When n is exactly equal to 0, this is 1, but this is alpha to the minus 1 underscore, which according to this is 0. So that is in fact correct. And when n is strictly positive natural number, then this just coincides with the usual formula, except that the n factorial here and the n minus 1 factorial sort of combine to take care of that extra factor of n that you get when you differentiate, right? There's really sort of an n factorial on the bottom here, if you like, and there's really an n minus 1 factorial. We're just not writing them. And so if we just multiply through by those n factorials that we are not writing down, we just get an n over here, because the n factorial on the top and the n minus 1 factorial on the bottom would just give us an n. So this recovers the usual formula. But that means we have a consistency of notation. We have one of these guys for every integer, and the capital derivative operator now just takes one of them and sends it to the previous one in this ladder, okay, with no exceptions, right across the board. So for example, if you want to apply d squared of alpha to the n underscore, you get alpha to the n minus 2 underscore. And again, there's no need to separate into, well, in this case, if n is positive, we do this, and if n is 0 or 1, we do something else, and if n is negative, we do something else. It's all just taken care of. Okay, so now it's not a big step to just extend our sort of mixed derivatives. So if m and n now are integers and k and l are natural numbers, then d to the kl, remember that's short form for d sub 0 to the k, followed by d sub 1 to the l. Those in fact commutes. It doesn't matter which order we do it in. So here now is one of these sort of factorial terms, but there's actually a product of this factorial polynumber times this factorial polynumber. So there's actually an m factorial that's missing, under here, and there's an n factorial missing under here. So this is what another way of saying what this thing is. And the result is just that, well, we're differentiating the alphas k times, so the m is going to go to m minus k. We're going to get alpha to the m minus k underscore. And the beta is being differentiated l times. We get beta to the n minus l underscore. And there's no need for any particular statement about special cases. And in particular, with our Laplace operator, which is d sub 0 squared plus d1 squared, when we apply that to one of these sort of mixed factorial polynumbers, so bi-polynumber, Laplacian acting on alpha to the m underscore times beta to the n underscore, well, the d0 squared is going to take this alpha to the m underscore and send it to a alpha to the m minus 2 underscore, leave the beta to the n underscore where it is. And then this d1 squared is going to do the same kind of thing. It's going to leave the alpha to the m underscore where it is and send the beta to the n underscore to beta to the n minus 2 underscore. So the action of the Laplacian on the bi-polynomials in this basis is particularly sort of pleasant, okay? Because somehow the factorials that are floating around take care of the various sort of exponents that are dropping down when you take repeated differentiations. Okay, so now let's have a look at an example. So here is a bi-polynumber written in this factorial form, and we're taking the Laplacian of it. Okay, so Laplacian of alpha 3, or alpha cubed underscore beta squared underscore plus 2 alpha to the 1 underscore beta to the 4th underscore. Okay, well, the Laplacian is linear, so it's going to be the Laplacian of this first term plus 2 times the Laplacian of this second term. And what is Laplacian on this thing? Well, you lower the alpha exponent by 2, so the alpha to the 3 becomes alpha to the 1, but still an underscore. Leave the beta where it is. And then you have another term where you lower the beta by 2, giving us beta to the 0 underscore, which is just 1, and the alpha to the 3 underscore remains, so there it is there. When we apply the Laplacian to alpha to the 1 to the beta 4th, when we drop the 1 here by 2, we get alpha to the minus 1 underscore, and that's 0. So that first term is 0. And then when we drop the 4 by 2, we get alpha to the 1 underscore beta squared underscore. So all together here, we have an alpha to the 3 underscore plus 3 times alpha to the 1 underscore beta to the 2 underscore. Okay, so now we are in a very happy position to more systematically understand how we get harmonic bipolynomials. And so let's have a look at what happens when we look at degree 4 things, but we're just going to look at homogeneous terms. So terms whose total degree is 4. And there are 5 of them. So there's alpha to the 4th, alpha cubed beta to the 1, alpha squared beta squared, alpha beta cubed, and beta to the 4th. But we're considering the factorial versions of all of those, okay? So there's a 3 factorial, 1 factorial really under in the denominator here, but we're just not writing it. Okay, so we want to think, what happens to these 5 individual terms when we apply the Laplacian operator to each one of them? Well, the alpha to the 4th underscore, what's going to happen? Well, it's just going to drop by 2. We're going to get an alpha squared underscore. You can't see it. I'll show you the next one here. We can probably go right to this one here. Okay, there we see what's happening. So the alpha to the 4th, we apply the Laplacian, we just get alpha squared underscore. How about this one here? Well, the 3 drops by 2 to give us alpha to the 1, beta to the 1 underscore. And the 1 drops by 2 to give us a minus 1. So that's sort of going in that direction, but there's nothing there because that's 0. This alpha squared, beta squared with underscores, the 2 here, if we drop that, then we get a beta squared. If we drop this 2 by 2, we just get an alpha squared with underscores. So the Laplacian acting on this thing is actually the sum of this term and this term. So each of these arrows indicates a constituent in the Laplacian, so with positive plus sign. So this thing plus this thing. When we take the Laplacian on this, well, we get alpha to the 1, beta to the 1 underscore, and the Laplacian of this is this one here. Okay, so now we want to ask, under what conditions can we cook up coefficients of these 5 terms so that the end result is 0? Okay, end result is 0. So suppose that there's an alpha to the 4th underscore term. So when we apply the Laplacian, we're going to get this thing here. But we want to get 0. So we want to cancel this alpha squared underscore that we just got. So we need to cancel it by having one of these guys in the original with a minus sign. There has to be a minus alpha squared underscore beta squared underscore. That will then contribute a minus 1 here, but it will also contribute a minus 1 of these. So to cancel that one, we have to have a plus 1 of these to cancel the minus beta squared that's coming from here. Right? So the combination that we require is an alpha to the 4 underscore minus alpha squared underscore beta squared underscore plus beta to the 4th underscore. But there's another possibility when we look at the other terms that we haven't looked at, these 2 terms here. The Laplacian on this one is this thing here, and the Laplacian on this one is also this thing here. So if we want to have a result of 0, we have to take a difference, this one minus this one. So there's the second solution. And of course, any combination or any linear combination of solutions is also a solution. So there's not just 2 solutions. There's actually a two-dimensional family of solutions given by multiples of this solution added to a multiple of this solution. But in particular, there's a two-dimensional family of homogeneous degree 4 bi-polynumbers, which are harmonic. Actually, that's the same thing that we found for the degree 3 case as well. In fact, also the same thing that we found in the degree 2 case. And also, actually, same thing we found in the degree 1 case. How about the degree 5 case? Well, in degree 5, here are the 6 basis homogeneous bi-polynumbers of degree 5. And the action of the Laplacian is pretty predictable, right? This alpha the 5 underscore goes to alpha 3 underscore. This one here goes to this one. This one here goes to a sum of this alpha cubed and alpha beta squared with underscores. This one here goes to a sum of this one and this one. This one goes to this one. This one goes to this one. It's exactly the same story. In order to have cancellation, if we're going to have an alpha to the 5th, we have to have a minus one of these, and then we have to have a corresponding plus one of these so that everything cancels and the result is 0. So that's one solution. And so the odd ones, if these are the even ones, the odd ones, a combination of this alpha to the 4th beta and this alpha squared beta cubed and this beta to the 5th, we need plus one of these, a minus one of these, and a plus one of those, and we get our second harmonic homogeneous bi-polynumber of degree 5. And once we've gone through these examples, it's completely obvious that this is pretty well the general story, right? For any degree, it's going to be exactly the same story, exactly the same picture of these back and forth cancellations. We have to choose every second one of these factorial polynumbers with a plus and minus coefficients. So in general, for a degree equals k, so homogeneous polynomials of degree k, there will be a two-dimensional space of bipolys p of that degree satisfying the harmonic condition, unless k equals 0. In case k equals 0, well, in that case, the space is spanned only by the constant function 1. And so now a great exercise is to just convince yourself that, if we do temporarily adopt the cosine theta and sine story, and we sort of identify cosine theta with alpha and sine theta with beta, that what we're really recovering here are exactly the usual Fourier constituents. 1, cos theta, sine theta. Those are the linear ones that we found, like alpha and beta. And here's cos 2 theta and sine 2 theta. That's like the alpha squared minus beta squared and the alpha beta ones up to a multiple. And then, and then there's the degree 3 ones, cos 3 theta, sine 3 theta, and then all the way up to the degree k ones, which are going to be cos k theta, sine k theta. So convince yourself that those expressions of the alternating factorial bi-polynumbers that we got is really just another way of sort of writing these things here, but in a finite algebraic fashion without any reliance on transcendental functions. Okay, so that's great. We're in a happy position. Basically, we've now got the basic ingredients of traditional Fourier series, but in a rational form. But there's actually something even more exciting ahead of us, where we meet for the first time a really remarkable aspect of quantum mechanics, which is that complex numbers, for some crazy reason, seem to be playing an integral, crucial aspect in our understanding of the quantum mechanical world. Why is that? Well, one kind of direction of explanation is exactly here when we're studying the simplest and most, arguably, most fundamental kind of non-trivial kind of curve, the circle. It will turn out that there is a variant to what I did today, okay, which is dramatically simpler in many ways, but it requires this contact with complex numbers. And it's really a motivation for why complex numbers naturally appear in the quantum mechanical world.